Hi, my name is Robert Feranek, I'm from FEDEVEL Academy, and in this video we are going to have a look how signals travel through your board, through your PCB. Maybe you remember a couple of weeks ago I created this video where we were speaking about how signal travels through your PCB, and when I was creating this video I was thinking like, it could be really awesome if we could actually see how this signal is traveling through this track. And then I noticed one of the comments, this one from Peter. He mentioned Yuri from Simberian, and he also attached this video. This is the video here. And when I was watching this video, I was thinking like, this is exactly what I wanted to show here. This is exactly what could maybe help many people to understand what is actually happening on your PCB, how these signals are traveling through your tracks. So I contacted Yuri and we had a call together where we discussed what you can see on these simulations. And this discussion, this call is what is going to be in today's video. So here it is. Here is my call with Yuri. To be precise, we are not going to watch the whole call because it's almost 2 hours long. What I'm going to do instead, I'm going to point out the most interesting parts from this call. And we are going to start with this simulation which we can see here. And this simulation shows electric field around the tracks. On this picture you can see differential pair routed on PCB. There are 2 tracks, one is the positive, the other one is the negative signal of differential pair, and there is also a reference plane here below the tracks. The reference plane is not visible, but it is there. We are running signals through these tracks. Can you guess what kind of signals we are running here? Sinus signal. Can you see where this sinus signal is crossing 0? Somewhere here in this place, which is here, okay? The green arrows is the electric field. So here where the sinus is crossing 0, there is no electric field. That's why the arrows are not here. The higher or lower voltage is there, the bigger the green arrows are. And the direction of the arrow is also important, okay? It shows you the direction of the electric field. You can see the arrows which are on this track, they are pointing up here, and on this other track they are all pointing down here. And then how the sinus goes on the other side, here you can see they are pointing up, and on this other track they are pointing down. To understand a little bit more about the electric field, you can just Google for it, but I will try to very simply to give you an idea what is it about. So when you have a wire and there is some voltage, then this voltage is not going to immediately disappear. This voltage is not only in the wire, but it is also around the wire. And a very good example are these power lines, which you can see here. Here are some pictures with the electric field around the power lines. So when you have very high voltage transferred through these power lines, here are different power lines, then you can see that even in some distance from the power lines, there you can measure there some voltage. Down here is a graph which shows you the voltage, and you can see, for example, even when you are like 25 meters from the power line, you still can measure, or there still can be like 100 volts. Okay, So this is important. When you have a line or track or something and there is some voltage, this voltage is not going to just disappear when you are away from the track. There will be this electric field around the track. And this electric field, it may look different, depends on the situations. So here are some examples. Let's say you have a ground plane and then you have a track routed about the ground plane. So this is how the electric field is going to look. You can have like differential pairs. One is positive, the other one is negative. Positive signal, negative signal. This is how the electrical field is going to look. And what is also maybe interesting, have a look on these equipotential lines, because these will tell you, or this can show you basically how this voltage is disappearing further and further you are from the line. The voltage is lower and lower. Okay, so these equipotential lines, they are showing you the distance from the line where the voltage is exactly same. So everywhere here, around this line, around this wire, for example, everywhere here will be the voltage, the potential will be exactly same. When you go a little bit closer, the potential will be a little bit higher. And you can see further and further you go from this line, the voltage is going to be lower and lower. The higher voltage is just around the wire, and then it goes rapidly down. So this is something what is important to understand. That's why we are running this simulation, because we would like to see this electrical field around the tracks, so we can see what kind of area around the track is influenced with this electrical field of the signal which is running through the tracks. When we go back to the video, this is what Yuri was telling me about this simulation when we had the call together.
So electric field is spatial presentation of voltage concept. Mm-hmm. That's how I usually explain it to anyone who knows circuit theory.
Okay, I'm going to move this.
Yes.
So this is the electric field.
Electric field, and it propagates. You can see plus and minus.
Yeah, here are the directions.
Yes, this is direction. Every arrow corresponds to, you see the scale here is in volts per meter. Mm-hmm. Right here on the left side, 4,281 volts per meter. This is when we launch 1 volt 100 ohm signal into this trace. That's how it what strength of the electric field is. So that corresponds to 1 volt signal, approximately. Structure. So with the modeling, and this is computed right below the traces. So.
Okay, we know how this electric field looks around the traces. Now we would like to know the current. We would like to see the current. I moved this video a little bit ahead. Now we are looking at currents. You can see it here. And this is what we were speaking about. And this is showing the direction, like this way?
Yes.
So here it travels this way, yeah?
Yes.
And on this trace it travels this way.
Travels this way.
Exactly. And in the plane it travels under this track, it travels this way. And in the plane here it travels this way, yeah?
Yes.
I really like this picture. I really like this simulation, because you can very nicely see how the currents are flowing through the track and how this return current looks in the reference plane. Yeah. So watch these triangles. These are showing you the direction of the current here and the direction of the current here. I can play the animation a little bit so it looks even a little bit more cool. Okay, we know the voltage, we know the current and what we can calculate from this. Power. That's what we see here, okay? Have a look on this diagram. We are looking at the power around the tracks. Again, I'm going to play a little bit from the call so you can see what we were talking about, or you can hear what we were talking about.
Yeah, the currents was flowing in a different direction. It's really difficult to understand what's going on. The voltages or electric field was going in the opposite direction on the traces, but the power is flowing in the same direction. This is differential signal. If you think about your differential signal and where's the energy of the signal, that's where the energy, it's the highest energy is around those edges of the trace. So notice those two kind of.
So that's why we see this and this.
Yes, yes. Those are edges of the trace, and both left and right trace, they have equal amount of energy propagating along them. You see?
Okay, and this energy is basically what, current multiplied by voltage, or?
Exactly, exactly. In time, animated in time.
Okay.
Total current by total voltage. But right here, it's also it's a distributed concept of the power and circuit theory.
I'm going to skip a little bit ahead so we can see different kind of view on this power, on this energy around the tracks, and I'm going to play it.
And this is you see, I added power flow density in the cross sections.
So this is just so we can nicely see.
Actually see that the power flow not right below, only below the traces, but in some area around the traces, and so it's a volumetric kind of thing.
Okay, so here we can nicely see that there is the reference plane, because the power only goes down here and that's it. But above the trace it goes away.
No, all above the trace it also propagates along the trace. It also propagates along the trace.
But it goes much further from the trace than if you have a reference plane.
At some distance above the trace, if you visualize it with arrows, the arrows will still point along the trace. So if you think about it's not a radiation. If you put a discontinuity in this area where the power propagates along the trace, the discontinuity will basically distort the field and power will start radiating in different directions. That's why if you put a microstrip traces on top of the board and something get into this near field area, the microstrip starts radiating. That's why people do not like microstrip much. So they really kind of prone to different defects related to microstrip has relatively far spreading fields.
So this is what can cause problem during EMC and EMI
exactly.
testing.
If something gets into this area from on exterior of the board, then it will create discontinuity and it will basically the even differential signal will start radiating. So it will start kind of spreading around.
And there is one more interesting part from the call when we were speaking about this situation. So let's have a look.
This area where the power propagates, that's area where you don't want anything in this area. If you put some vias over there, if you put cutouts in the ground
plane, here?
Yes, where it's still green. And if you put some other traces in this area, then you'll have some kind of interaction, coupling.
So this is basically, you can imagine this like the field around the track, which cannot be disturbed.
It's a product of electric and magnetic field.
Yeah.
A vector product of electric and magnetic field, simultaneously electric and magnetic field. That's what good about power flow density. You see simultaneously electric and magnetic field. Basically what they produce in terms of energy localization.
Does it mean that, for example, if you are routing two signals in parallel above of each other, it is even worse comparing to situation if you route them like on one layer, but you know,
worse. And my last demo video actually about this, about routing at different levels, and there you'll see that the one trace had much larger spreading of the energy towards the other trace when the reference planes kind of far apart. So the last demo video I posted last week probably was about this coupling in different layers.
If you would like to know more, go on Simberian website. Okay, so these are the videos what Yuri is talking about. You will find them here in demo videos. And this is the crosstalk simulation when you have tracks routed close to each other and you can see this coupling on this track which is here. But also other videos are interesting and you can learn quite a lot, and maybe you can also start understanding some of the stuff what you maybe even didn't notice before, and then you will see, that's why they are doing it. Have a look on this opening around the vias. Okay, when you see the fields, when you see the power or energy flowing through these tracks in the simulation, you will see why this opening around these vias looks like this. Why these openings are not just two circles. Yeah, so just watch some of the videos and maybe it can help you to imagine the signals on your board a little bit better. In the next part from the call, we are going to speak a little bit about different situation. This is the situation when we bend the lines. So I'm going to play the video.
What is the power?
So, but if we don't bend this, then it would look nice as it was initially here in these pictures.
Mm-hmm.
Everything what we can see, all this distortion, it is caused because it is bending.
Because of its bending, yes, it's discontinuity.
Mm-hmm. Because when you say discontinuity, it is because of the.
It's not a straight line.
It's so not okay.
Yes, when we look at like a piece of transmission, piece of trace along the over the plane, this is that structure can be formalized, formally described as a transmission line with a very high precision, up to very high frequencies. But when you start bending it, even like turning it left, right, that's already discontinuity. Mm-hmm. Even single trace, when you bend the single trace, it's already discontinuity. Mm-hmm. So the signal not propagating straight. Again, for single transmission, single trace, it's relatively good approximation to still have a transmission line model, even if it becomes if it goes like serpentine, then it may become coupled to itself. Mm-hmm. Then different models.
Yeah, I've seen some people what are doing the serpentines and they do it even closer than
than it's the. And then it couples to each other and energy propagates kind of faster along the whole structure. So
when we say serpentines, these are the waves. Yeah, when you do, for example, length tuning. So some people they make the waves very close to each other. So that's what we were speaking about.
But in case of differential, even simple bend becomes a discontinuity, and that's what you see here.
So discontinuity will cause all these weird shapes in the signals.
Yes, and right here you clearly see on this band we've got a little bit of reflection and we've got considerable mismatch of the energy propagating along each trace. So if we look at them separately, you'll see now they are kind of a different location in space.
Yeah.
They originated at the same level right here.
But
at the end you see them considerably kind of a different point in time in space, time-space.
And now you may think, when we bend the differential pairs, then one signal is a little bit shorter, the other one is a little bit longer. That's why these signals will not arrive at the same time. So what we are going to do, we are going to add these bumps, to make this shorter signal a little bit longer. Not so simple. Have a look.
Right here it is done almost right. The compensation was done very close to discontinuities, except the last one. The last one at the bottom. This loop was relatively far. And what happened after the last bend or turn on the left?
So it should be somewhere here, yeah?
Yeah, it should be somewhere here. And the reason is...
So basically what we are talking about is notice how these zeros are traveling together everywhere here. And it's because, here is the bump, so it's almost traveling together. Again, here the tracks, they are bending, so here is another bump which is compensating the length of the traces. It is traveling together, and here is another place where the tracks are bending, and this is the place where the difference is happening. And this last bump, which is here, it should not be here. It should be where the tracks are bending, where this discontinuity appears. So this bend should be placed here. So these zeros, they travel together. And as you can see, in these places, they do not travel together, and these places are the problems. Because in these places, the signals are not like plus and minus. In these places, they are both like plus, or minus. That's the problem. But listen.
When two modes are traveling this piece of transmission line, even an odd mode, they have different velocity. So even mode goes slower, even mode goes slower, and differential goes faster. And then they becoming out of phase very quickly, and then...
So it means in these places, the signal will travel different speed than in these places. That's the problem. And now, something what was really interesting for me. In some cases, it is very difficult to length match these positive and negative signals in differential pair. So in some cases, it is very difficult to add enough bumps to make the length of this positive and negative signal exactly the same. And what I sometimes do is that in these special cases, I create one of the bumps a little bit bigger. So I don't have to do many small bumps. But this is what Yuriy say about these bigger bumps. So when we would make this bump a little bit bigger, it means when you say discontinuity, it means it introduces some kind of noise on this signal which has this bigger bump?
Yes, a bigger bump will produce larger reflections.
What? I have been doing it wrong. See, we all learn all the time. Even I learn some new stuff all the time. Next time when I will be doing layout of differential pairs, I should be much more careful. Probably I should not be using these bigger bumps. So that's something really, really important from this call, and I really hope it is also something useful for you. Now the question is, when I was using these bigger bumps, I have never seen any problems. Why? Listen what Yuriy is going to say.
At data rate, so at lower data rate, below 3-5 gigabit per second, it basically doesn't matter. So
this means that if you are designing boards or interfaces which are up to 3 or maybe up to 5 gigabits per second, you still may get away with some small things which may not be perfect for the layout. But if you are going to design, or if you are designing boards or interfaces which are with data rate which is above, for example, 10 gigabits per second or 20 or 30 gigabits per second, if you are designing something what is about 5 gigabits per second, then you may need to be extra careful. Okay. When you will be designing this kind of boards, this kind of interfaces, maybe study a lot of document and read and watch some videos, maybe do some simulations so you understand better what is actually happening on your board, because it can help you to understand why you are doing some specific things and why it is important to do the layout properly. Okay, we are almost finished. Here is the last thing what I would like to show you from the call, so I'm going to play it.
That's really crazy structure, but that's again real board. You can see coupling here on the pods. Pods are coupled to trace itself. You can see the energy basically jumping from the
here?
pods. Yes, from PCB pods.
So the energy from this pod, it goes here on the track.
Yes. You cannot see it, but you can basically say, okay, that's what probably happens here. You can see that something going on in there, and that's coupling. Yeah, right here.
And it means it will disturb the signal.
Yes, it will. Your signal will not look like you want it to look.
Because something really from what should be there a little bit later, it is coupled in different time on signal which is coming in different time, yeah?
Exactly, and you can see, you can clearly see stronger signal on the trace that is closer to us.
Here?
Oh, here. Yes, and
so this is a little bit lower.
Exactly.
And here it is a little bit higher.
No, the closer to the end. Closer to the end, you can see on one trace
this one.
Closer to this one. Yeah, you can see the color is much
red.
More red. Yes. And that basically means that you pump more energy into this trace. And this is a dB level, so in reality it may be quite a lot of common mode signal over there. So I put different scale on it, and you now see how, well, that's a bad case.
So this is little bit red, little bit more red than this other signal. It
exactly.
means it pick up the power of
high
in this
power
places.
propagating in this interior trace.
And it means when it arrives to the receiver will have not same signals, but one will be a little bit bigger and the other one will be...
Exactly, it's a superposition again of differential and common, so essentially you're losing energy in the differential and getting more energy in the common, which is useless. So you're losing energy from the useful signal.
Okay, that's everything for today's video. Don't forget to check also the other videos from Yuriy. Go on this Simberian website and have a look. They create this software for the simulation. If you click on the order form, you can see also the price list, how much it costs. This is not the promotion of the software, but even I was interested to know how much it would cost me to have this kind of simulation software. So that's why I wanted to show it in this video, because maybe also it is interesting for you. And if you would like to see a simulation of some specific examples, specific situations, then maybe I could contact Yuriy again and we could maybe make more videos. But first we would need to see if you like this video, if people are interested about this topic, and if yes, then we can create more videos. So don't forget, if you like this video, press like button and also leave the comments because I would like to know what do you think about this kind of simulation, and let us know if or what you would like to see in the future in this kind of simulation. Thank you very much for watching, and see you next time. Bye.